All right, in this video, we're going to learn all about sets. So when we were looking at the real numbers, we were already starting to use some notation, but we're going to have some names to go with that notation. So if we're just going to list the elements in a set, we call that the listing method, which we saw when we were listing the natural numbers. I'm going to actually close this set off and make it end with 4. But this is a set. It has 4 elements. So each of those numbers is an element of that set. Set builder notation was when we had to describe what the numbers were like. And you can actually sometimes use the listing method or the set builder notation when you want to describe a set. But for example, in the rational numbers, we couldn't actually list that set. So this set builder notation is really good when you can't actually list it or it's too time consuming. It's much easier to just write a rule. But if I wanted to write the set builder notation for that set that we just wrote, the numbers 1, 2, 3, and 4, what I could say, again, curly brace to say it's a set, I'm going to write x is my element. You could really use any variable here. I just use x because that's a common one. And let's think about a rule to describe those numbers that are in the set. So the first thing I notice is that they're all natural numbers. And so I could say that x is in the set. So this little notation means it's an element of, or it's in the set. And I'm going to write something fancy, n. Remember, that was the notation for the natural numbers. So it has to be a natural number, but then we notice it doesn't keep going forever, so we're going to say the word and to give it a second rule it has to satisfy, and that is that your x's are less than or equal to 4. And so that's only one way to describe that set, but it is for sure equal to that set. And maybe you came up with something different. So let's look at some examples of sets that are in the listed, using the listing method that we can write in set builder notation. So we have the set 2, 4, 6, 8, 10. Well, that sounds kind of familiar. Those are all even numbers. So let's write this in set builder notation. We'll say it's all the x's such that, let's see what x has to be. It's even. And it's a natural number, so we could put x's in n again. Or you could write the words, but it's nice to use those symbols. Now, another way to say that x is even is you could say that x is equal to 2 times n, where n is a natural number. You could say something like that too. So this is just another way to represent even, because even means that it could be divided by 2. Now, I'm also using this bar, which I didn't define earlier, which remember is just a little break between the element of the set, but we can read it such that. So it's all the x values such that, and then you list the rule after. That's the set builder notation. And that's what I just did here. It's all the x's such that, so in other words, it's a number such that x has to be even and a natural number. So I've just defined that set. So now I have 1, 4, 7, 10. Well, they're not even, well, they're not all even, they're not all odd, but I do notice that within this set they're plussing 3 every time. And so I could say, okay, well, let's say this is the set of all the x such that, let's see, so you start at 1. This is our starting number. Let's think a little bit more about what's happening here. Thinking back to our arithmetic and geometric sequences, it's adding 3. So to get to the second term, it needed 1, 3. So if I want to know the nth term, that could be found by starting at 1 and then adding, remember it was 1 less than wherever you are of those 3's, which can actually simplify. It'll be 1 plus 3n minus 3, so I guess we could write 3n minus 2. So that's kind of a rule we could say, that it's all those x's, as long as the x's look like that, they have to be in that form, because those are what the elements are. And again, we know that n is in the natural numbers. Remember, if you do define a new variable in there like n, you have to say something about it. And so that's that second part of our rule. You could also have written it just another way, that it looks like those 3n minus 2's and such that your n is in the natural numbers. That's just another way that you could write it. Now we're going to go the reverse way. We have some set builder notation that we need to write as a list of elements. Now one thing I noticed right away in A, there's a little typo here, this should have been a k, sorry about that, because we had a variable k here. So it says it looks like that form, 2k plus 1, where k is in the natural numbers. So if we want to start listing that, remember the natural numbers are 1, 2, 3, 4, and so on. So if I put a 1 into this expression here, that's going to be 2 times 1 plus 1, which would get a 3. If I put a 2 in there, that's going to get me a 5, right? I'm doing 2 times 1 plus 1 equals 3. 2 times the 2 plus 1 equals 5. You could plug the 3 in, 2 times 3 plus the 1. You could plug a 4 in, and you could keep doing this forever. So we're going to put a little ellipses on there. 3, 5, 7, 9. Really, these are the odd numbers starting with 3. I'm going to close that off, and I just made my list. Now we have x, such that x is an even natural number. So it's even. We know what that means. Natural numbers, we know. And it has to be less than 10, though. So less than 10 means not equal to 10, but strictly less than 10. So this list here is going to be starting with 2. That's the first even natural number. 4, 6, 8, and we don't want to include 10 because it said less than. Not less than or equal to, but less than. And there's our set. We just made our list. Now one word that you'll see in relationship to sets is the word equal. 2 sets are equal if they have the same elements. Now a set has no order to it, so just so you know, if we write 1, 2, 3, this is actually equal to, and we use the equal notation that you're used to, like 2, 3, 1. The order doesn't matter. Or some other variation. You could even put, I don't know, 3, 2, 1. These are all equal sets because, again, order doesn't matter. It's not like an ordered pair where you need the first and then the second. It's just a set of stuff, so order doesn't matter. All right, flipping over to the next page, we have something called a one-to-one correspondence. If the elements of one set can be paired with the elements of another set, so that for each element, the first, there's exactly one of the second, and vice versa, we say that there's a one-to-one correspondence. So for example, if I have set A, which is the numbers 1, 2, and 3, and I have set B, which is these names Julie, Jamie, and Chris, we could show that they have a one-to-one correspondence by mapping each element in A, so 1, to a name. So 1 will be Julie, 2 will be Jamie, and 3 will be Chris. So you've been able to associate each element in set A with an element from set B, and so you have shown a one-to-one correspondence. Now, I could have done that in lots of different ways. I just happened to do like first with the first, second with second, and third with third, but it could go a variety of different ways. So for this next question, it wants to know, well, how many one-to-one correspondences are possible? Well, it's basically you're assigning, and I'm going to draw this with something called a tree diagram. You're assigning an element from the first set, so the element, we'll say 1, 2, and 3. You're trying to assign those to the elements in set B. So let's think about, okay, I'm going to start here, and I want to come up with one of those correspondences. So I could assign number 1 to Julie, which is what I did, so that could be like the path I take. And then from there, I could choose, who did I choose? Jamie. And then from there, I would have to choose Chris. But I didn't have to do that. I could have chosen the first person to be Julie, Jamie, or Chris. And then once I chose that person, there's actually, I made Julie go and then Jamie go second, but it could have went Chris second. But if Jamie did go, then Chris has to follow. If Chris went, then Jamie would be in here. Now, if I started with Jamie, then that could go to Julie or Chris. But if it went to Julie, then Chris would have to be next. If it went to Chris, then Julie would have to be next. And then similarly, if it started with Chris, then it would go to either Jamie or Julie. But if it was Jamie, then for sure Julie would come next. And if it was Julie, then for sure Jamie would come next. And so really what we're saying is that the first element could happen 3 different ways, right? There were 3 different ways. The second element could happen only 2 ways because the first person was already chosen. So you can see that it was like, okay, there were 2 ways you could choose that or 2 ways to choose that once you knew the first guy. So there are 3 ways to choose the first guy, 2 ways to choose the second guy, and then from there, there was only 1 way to choose the third guy. And so what you have here, we have these little chains. And I will have 1 chain, 2 chain, 3, 4, 5, and 6. Really, you could just count the endings. 1, 2, 3, 4, 5, 6. So there were like 6 paths that you could take, or really we could say that there were 6 one-to-one correspondences possible. But notice that 6 is made up of 3 times 2 times 1. There were 3 ways to choose the first guy, 2 ways to choose the second, and 1 way to choose the third guy. What that's using is something called the fundamental counting principle. And so if I look at the question here, it says, how many ways can you have a 2-scoop cone if 10 flavors are possible? So what you can say then is that there are 10 ways to choose the first flavor, and then there are, let's say you don't want the same one again, so then you'd say there were only 9 ways to choose the second flavor. And so we could multiply those together, and then we'd say that there are 90 ways, or flavors, there are 90 ways to make a 2-scoop cone. But if you don't mind the same flavor again, you could say 10 times 10, which would be 100 ways if you can repeat the flavor. So it kind of depends if you want 2 the same or not. It wasn't stated in the question if they were the same. Now, I used this fundamental counting principle, but I could have gone and done a chart and multiplied it the same way that I did for finding these one-to-one correspondences, because I could say, okay, well, there's 2 scoops, so first and then second. And so I could like have this starting point, and I'm going to 10 different options, right? So 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 different places that I could go. But then once I'm at that point, then I have 10 more ways that I could choose the second, 10 more ways that I could choose that one, and so on. So there's going to be 10 ways to choose that guy, and then 10 ways to choose that if I'm doing the one that had that repeated flavor. So hopefully that makes a little bit sense. Now, when I'm talking about equivalent sets, that's when there is, going back, that one-to-one correspondence. So that set 1, 2, 3 was equivalent to the set with Jamie, Julie, and Chris in it, because I can connect them one-to-one. And that's the symbol that we use for equivalent sets. So the difference between equivalent and equal. Equal, they have to have the same elements, like the same exact elements. Equivalent means really it's the same number. So that way you can have a one-to-one correspondence. And so you can come up with some of your own examples here. So now for this next page, we're going to learn a few more terms about sets. And we have them here bolded. We have the cardinal number, which is denoted with an N parentheses capital A. And really what that's saying, and why the notation is what it is the number of elements in a set A. The complement of a set, written as A with a little line above it, is the set of all elements that are not in A. The subsets, let's see what that notation would look like. If every element of B is an element of A, we would say that B is a subset of A. And so we've seen a few examples of subsets when we were doing our Venn diagram. I like to draw it with a picture to really see. So if B is a subset of A, it means that if B is the set of all this stuff, that it would sit inside of set A. Going back to the previous example here with the complement, if you want to see a picture, if you have A complement would be everything outside of here as long as it's not in A. Now a proper subset, and actually I need to go back to the last one, a subset could be equal, so they'll often put that little line under it, just like less than or equal to, it's similar to that. A proper subset is when you don't have that line, and so there's no way that they could be equal. So it's every element of B is an element of A, and at least one element of A is not in B, because we're saying that they're not equal. So now I'm going to give you a chance to use some of this new notation and these key terms and write as many facts as you can about these following sets. So we're going to say the universe, the whole entire big set, is going to be the letters in the alphabet. And then we have these sets that are given here, A, B, C, and D. And then we have the set E. So we want to come up with some different facts about these sets. So for example, we could say that A was a proper subset of U because it contains elements, all the elements in A are in U, because A is A, B, C, and the universe is all the letters in the alphabet. But A is not equal to it, so I don't have to write that little line under it. Now I could write, let's see, A is equal to C because they're the exact same elements. I could write that A was equivalent to D because they both have 3 elements, so I have that 1-to-1 correspondence. I could write the complement of E. So that's everything not in E, but you still have to stay in your universe. Your universe is the biggest set you could be. So notice that E is all of the alphabet except it's missing X, Y, and Z. So the complement of E is actually going to be set D. What else can you come up with? Think about if there's anything else that you could come up with. All right, so that was just a few of the possibilities. You should have come up with at least a couple more. So now we could actually talk about how many subsets are there for the following sets. So let's see. We have the set A, that has 1 element. There's actually a set, if I look at set B, that has 2, set C has 3. There's actually a set that has no elements, and that's called the empty set. I'm going to denote it with an E. And so we can write these curly braces, but there's nothing in it. Sometimes we'll even write it with a circle with a line through it. But again, we're going to call that the empty set, the set with nothing in it. So if we're trying to come up with subsets, we could say, okay, well, the subsets for set A is going to be, well, A, the set A. And then we could also say the empty set. Those are 2 possible subsets. Remember, it didn't say proper subset, so it could actually be it. Now for set B, we could say, well, that could be a subset with the set just A in it, or with just B in it, or we could put A and B in it, or we could have the empty set. For set C, we could put A and B, like put them all separate. Then we could put A with B, and we could put B with C, and what am I missing? A with C, so putting all the different partners together. And then we could put the whole set, A, B, C, and the empty set. So if you look at the number of sets as we keep increasing the size here, when we had one element, we had 2 subsets. When we had 2 elements, we have 1, 2, 3, 4 subsets. When we have 3 elements, we have 1, 2, 3, 4, 5, 6, 7, 8. And I want to go back one step. When we have the empty set, the only subset of the empty set is the empty set. So it's actually only one subset. So we have 1, 2, 4, 8. What do you think might happen next? Using inductive reasoning, I'm going to guess 16. It looks like it's doubling every time. So then if there's going to be 4 elements, we're guessing that there will be 16 subsets. And you could write them all out if you'd like. But basically, if there's n elements, if we're going to be doubling every time, this is really like 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power. So if there's 4 elements, there is 2 to the fourth subsets. So n elements, then there will be 2 to the n subsets. And that even matches with the very first guy because there's 0 elements in there. 2 to the 0 does equal 1. So if there were, let's say, 30, no, that's too big. Let's say that there were 5 elements. Then there would be 2 to the 5th, which is 32 subsets that you could come up with. All right, the next video we're going to learn even more about sets.